Hello everyone, I'm Paul and today we're solving problem 1625, lexicographically smallest string after applying operations. This is medium and the key here is observation. So let's start. We are given a string of even length with digits from 0 to 9. So let's say this is the string and we are also given two integers, a and b. And we can do these two operations any number of times to get the lexicographically smallest string that we can get. The first operation is we can take every add index, this is index 0, this is 1, so we take every add index and add the value of a. 5 plus 4 is 9, and digits post 9 are cycled back to 0. In this case, if we do the first operation, we get 79. And for the second operation, we can rotate the string to the right by b positions. Here b is 1, so if we rotate this to the right, we get 47. And we can repeat these operations, so here we have two more scenarios, here we have two more scenarios or different strings, and we need to return the lexicographically smallest string that we can get. For this example in particular, first we start from here, then we can rotate this, we get 47. Then we can do the first operation, so the first digit is 4, and given that this is add, we take 7 plus 5, and this is 12, but digits post 9 are cycled back to 0, so we can do 7 plus 5 modulo 10, and this is 2, so here we get 42. And now from 42 we can rotate this again one position to the right, so we get 24, and this is the minimum number that we can get. More specifically, it's the lexicographically smallest number that we can get, so we return 24. Here we have the constraints, and these are the key for this problem. The question here is how many different strings can we build in the worst case as a maximum. And for this we can have some number with 4 digits. Let's say this is index 0, this is 1, this is 2, this is 3. And for the first operation we can get 10 different strings. Okay, why 10? Because digits post 9 are cycled back to 0, so we can get 10 different strings. Regarding the second operation, in the worst case, if b is very small, for example, here is 1, so this is the worst case, we can rotate this n times. So we can have n times 10 strings. Now the thing is, if b is an odd number, for example here it's 1, after one rotation, now the new odd numbers are this and this. So for each of these we can get 10 more different strings. So this is times 10. And this is roughly big O of n squared, or 100 times n. And given that n is smaller or equal to 100, this is roughly 100 to the power of 2. And this is not a very big number. We can handle this number. What this means is we can try every possible string and return the lexicographically smallest. So let's explore every possible string. For this we will have a set that's initially empty, and we are storing every string here. First we have 74, so we can add this. And now we can do the first operation, so the result here will be 79, and for the second operation we get 47. These are not in the set, so we add 79 and 47. And we repeat the same process for these two. So this would be the final tree, this is the final set, and the minimum value here is 24, so we return this. And what we are doing here is a breadth first search. We are going level by level. First we are here and we explore the two possibilities. Next we are here. We add these two to the set and explore every possibility. Next we are at this level. Next we are here. And for example, these values were already in the set. So at this point we continue. For example, here we added 92, so next we are at this level, and finally we are at this level. So this is the entire approach, and with this in mind, let's go with the code. First we say n is the length of s, and remember that for BFS we need to use a queue, and in Python we can use a deque. We are using this because we need to pop elements from left. So initially we have s here, and sin is an empty set. We need to add the initial string, and the result is initially the initial string. And now while we have something in the queue, current is queue.popLeft, and the result is the minimum between the result and current. We need to keep the lexicographically smallest string. So now we can go with the first operation. We'll call this O1, and for this we can take a list from current, and for I in range from 1 to n in steps of 2. Remember, we are iterating every add index. O1 at I will be O1 at I plus A, and this is modulo 10. Remember, we only care about the last digit, and we need to transform this into an integer because it's a string, so we use this. And finally we transform all of this into a string like this. Now we can say O1 is this showing O1, and we are checking if not O1 in sin.add O1, and we add to the queue O1, so queue.append the new string. Now we can move to the operation number 2, and we do the same here. We take a list from current, and here we have a small trick to rotate strings. We can say O2 is a substring from -b all the way to the end, plus another substring from the start to -b. And now we do the same as before. O2 is showing O2, and we are checking if not O2 in sin.add O2 and queue.append O2. Finally, we can return result. So this will go on and on until the queue is empty, and we will keep the lexicographically smallest string every time. Finally, we return this. So this is the entire code. Now let's submit this and see if it works. This is sin, so let's fix this and try again. As you can see, this works and it's very efficient. Remember that time and space complexity here will be big O of n squared. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.